Welcome. So, in this lecture, we are going to talk about some basics of sampling under fixed and variable frequency modulation in switch mode power converter. So, in this lecture, we want to show the steady state operation of switch mode power converter. Primarily, we will focus on buck converter as well as boost converter. Then, we will discuss various fixed and variable frequency modulation techniques, and then understanding sampling method. How to, if you want to sample a particular signal, let us say we want to sample the output voltage, and when the converter is running under let us say fixed frequency modulation, then how to sample and what to sample, what should be the sampling rate. Similarly, when it is running under variable frequency operation, then how to sample. So, this basic concept will be discussed in this lecture, so that this will create a path, so that the next lecture we can go deeper into the actual control architecture, and then basic of uniform event based sampling. So, first we will consider a DC-DC buck converter, and in this converter it is a more or less realistic buck converter with it is an ideal buck converter, and here we are sensing the sense resistor, that means current inductor current through a sense resistance RS, and there is a current sense amplifier. So, we may or may not use this current feedback in actual control implementation, but in this lecture we want to show if suppose if it is a ideal buck converter, then this QH is nothing but same as Q, this gate signal, and QL is just the complement of Q. But in a practical buck converter or any DC-DC converter, we need to actually consider some dead time. That means there should be a gap, time difference between turn off of this low side FET and turning on the high side FET. There should be some difference in time, otherwise there will be a shoot through operation and it may short the supply to the ground. Now, to start with, let us consider that under trailing edge modulation, that means what is trailing edge modulation? The trailing edge modulation, that means we generally turn on the converter, this is an external switching clock FSW, and this will decide our switching frequency of the converter. Then the Q, which is the gate signal, it will be turned on or it will go high when the rising edge of the clock comes, and it will be turned off. So, suppose if we use a fixed duration. So, how do I generate this signal? One way you can very easily generate, suppose if you consider a comparator, okay, and there are two input to the comparator, and if you take here a sawtooth waveform like this, and here if you take a control voltage Vc, and this is a ramp signal, and this control voltage can be a number, and then you can add a RS flip flop R and S Q, this is your gate signal, and this one suppose if we sync with the switching frequency clock. So, this is my this signal, that means this is my FSW clock, which is shown here. So, now here if we use this control voltage, let us say we are talking about this is my control voltage, which is my Vc. So, naturally this will and this will generate this on time like this. So, by that way we can actually generate this on time. So, here it is open loop, that means we can provide a fixed voltage and we can compare the sawtooth waveform to generate the on time of this, and this is under pulse width modulation. Next question, I want to discretize this signal, output voltage signal. Okay, so, I want to pass through, that means we need to pass through a to D converter, that means this is my V0. So, I want to pass this V0 to an A to D converter. Initially I am not considering, it is like some sample voltage. Initially I am not considering the quantization effect. I am assuming that the quantization effect is neglected. I am just talking about the sample signal. That means how should it look like? So, let us say here again the same waveform, but now we are sampling this voltage once per switching cycle, because there is a switching cycle this is the duration of the switching cycle, and the time period is t. So, we are uniformly sampling, because this is under uniform sampling, we are sampling once per switching cycle using a fixed frequency clock. So, you can see this is the sampling clock. That means, if we consider an A to D converter, ADC, and this is my analog output voltage, and this red dotted one, let us say it is the sample voltage. So, this ADC require a clock, and which is my SM. Okay? So, it is a sampling clock. So, here the clock edge, at the right edge of this sampling clock, you will capture a sample. Now, here I am talking about the ideal sampler, but practically there will be a delay, because every ADC should have some conversion time. So, here if we sample the voltage, then it will actually sample like this. That means, it will be a zero order hold effect. That means, after sampling, A to D converter will also have a resistor. So, it will hold the value. So, it will behave like a zero order hold, and it will again update when the next sampling edge comes. Here we are sampling the signal, it is a periodic signal, and we are sampling in synchronism with the switching clock at the same edge. So, you can see that voltage is getting updated at this edge, and which is also the switching frequency clock edge. But earlier we took only one sample per cycle, but we can also increase higher sampling rate, and if you increase the sampling rate so high, eventually it will become like a continuous time signal. So, that you keep on increasing, you take 10,000 cycle 10,000 sample per cycle, it will almost behave like a continuous time signal. That means, inter sample duration is very small. So, here I am just showing a 4 sample case, where in between two edges, that means this is the switching clock edge and this edge. So, you can get 1, 2, 3, 4, you are updating 4 times. So, it is a 4 sample per cycle. Now, you may ask, that means, if you use again this ADC, and this is again your V0, and this is your V sample, again this is my V sample. So, this FSM, if you take the frequency, it is like 4 times of FSW, the switching frequency. Now, the question is whether we should choose 4 times, should we choose 5 times, 10 times, 1 time, or can we go even fraction, that means we can take 1 per 5 cycle, is it possible? So, this thing we will discuss when the architecture will come, because you will see in digital control, under steady state, the control variable which is coming out of the controller, we have not yet started that, it will become a fixed number. So, if it is a fixed number, and if there is no change in the output voltage, and if there is no change in the controller output, then I can say, why should I sample? So, I can just keep watching the digital ADC, and I can even may not sample at all, it will behave like an open loop system. So, in that case, we can reduce the sampling rate just to save power. That means, we are taking the sample, but we are not computing the digital controller, you are just keeping it idle and holding the value. So, that means, there are many possibilities that we can discuss. So, 4 sample is one case study where the sampling rate can be higher than the switching rate, but whether it is desirable or not. So, we will show some MATLAB case study in going forward, so that what can be the implication in the stability when such 4 samples are considered, because you will find there can be any small deviation in the duty ratio, it may lead to a high periodic nonlinear behavior because of this multi-sample. But generally the multi-sample, since you are taking more number of sample, naturally the voltage update rate is high, so you can reduce the delay. So, that means, this multi-sample can be helpful to reduce delay, loop delay, but at the cost of more power processing and all, and there are many research papers how to even interpolate the intermediate information, because you are not getting the information between this and this point, so you can interpolate. So, this possibility can be there. So, but we are not going detail, we are just throwing so that you can think about this, whether it is possible to 4 or 5, we will discuss when you consider the MATLAB case study. Next, but as I said, the delay, that means if you consider a simple ADC A to D converter, which is my V0 and this is my V sample and this is my sampling clock, this is my sampling clock, this one. Now, I want, you can see here as if we are providing the sampling clock here. Why? Because we are still not considering the delay of the conversion, we are just showing the sampling clock. It is just for the concept, because here we are using the sampling frequency and the switching frequency same, they are exactly same, but there is a time shift. That means sampling is occurring earlier than the switching event takes place. Why we are showing that? Why not same time? What is the problem at the same time? We will see in the subsequent lecture that you will have some time, require some time for the conversion. That means ADC requires some conversion time, right? Conversion time. This is for the ADC. Plus, you also need some computational time for the digital controller. And this delay, which is TS delay, this delay is provided to accommodate the total conversion time, so that your actual control voltage or control current, whatever architecture will take, that should be available. That means sending the command to the ADC for getting the sample at this point, but the actual sample may be available after some delay, and then taking into account the controller computation, your actual reference current for the current mode control or the voltage for the voltage mode control, the actual control voltage may be available after some time. So, taking that into account, we need to play with this sampling clock. That means this sampling clock, it is the frequency wise, the sampling clock, the frequency, if you take the frequency, it is same as the frequency of FSW, but there is a time shift, and we have to play with this time shift to accommodate this practical delay, and this time shift will introduce this delay, which can vary. In fact, if you are going for low power, it may so happen, because you need to save efficiency, this delay can be few switching cycle, it can be more than one switching cycle. And there are different kind of hardware as well as software control architecture. For hardware control, if you go for ASIC, you may try to reduce the delay by optimizing the hardware, but when you are talking about a digital system solution, suppose you are using a microcontroller from one vendor, then you are using ADC from other vendor, but you need to interface. So, to make the whole thing work, taking into account different computational time, sometimes the software control you may take one switching cycle delay, and that is exactly what is the one cycle delay. Here you can see the voltage is getting updated, but you are getting sample here, but you may use that data in the next cycle. That means if you take the sample during nth switching cycle, at the beginning you will need to use the data, that means the conversion time and computation time. After that, the data will be ready at this time onward, this cycle, and that is called one cycle delay. So, unless we close the loop, we will not see the effect of one cycle here, as if we are just showing the sample version, but we have to use this sample information into the controller, then only we will get the full picture of the one cycle delay. But the bottom line is this one cycle delay is used to sufficiently accommodate the conversion time and the computational time, but this will also penalize in terms of loop delay. This will penalize heavily in terms of nonlinear phenomena, and we need to tackle how to make sure your design you can make your design stable even with this delay. And then what could be the alternative arrangement even with this delay, because you may not need a very fast ADC. One possibility, you may increase the sampling rate when there is a transient, or you may create an additional path to bypass to avoid such large delay during a large transient. So, there are many possibilities exist. Now, coming back to constant off time modulation, where the off time is constant, but on times vary because we have learned this thing. On time vary based on the feedback comparison. So, that means feedback means constant off time means generally if we implement a peak current mode control version of constant on time, inductor current is rising and then it is falling, rising, falling. So, you see this is my off time, that means this duration is my T off, and if we keep the off time constant, then once the off time is elapsed, we generally implement using a monoshot timer, and in this course we will implement this monoshot timer using HDL code. It will be very interesting, it will be a counter based approach. So, you can implement once this timer is elapsed, then your switch turns on and switch will continue to turn on, remain turned on until this inductor current hit the peak current limit. This is my peak current limit and this is my inductor current. Once it hit the peak current, again switch turns off and it again the monoshot timer is activated. Now, since this is a variable frequency modulation, because your off time is constant, but the on time will vary based on the variation in the initial condition, variation in the peak reference or many disturbance. How to sample? Because the time period can vary, even with a small perturbation the time period can vary. If we use an uniform sampling, then you see sometimes the sampling can happen here, sometimes the sampling can happen close, sometimes sampling can happen here. So, that means duration between the sampling point and the turn on time, that will differ, because there is a mismatch between sampling instant and the switching instant. It is natural because you are using a fixed frequency sampling clock, where your switching clock, whatever, I will not say switching clock because there is no switching clock, it is a trigger clock. I will say trigger clock because this trigger clock is enabled once the off time is elapsed. That means once the timer complete the timing, then this trigger pulse comes. So, this trigger pulse is actually an event, it is not associated with any fixed frequency synchronized clock. But now the question is, if this time period varies, then fixed sampling rate, naturally there will be always a mismatch between the timing, that means the sampling timing and the switching period. Sampling period and the switching period, there will be always a variation, and we will see such control when you actually implement in MATLAB, it will lead to something called multiple limit cycle oscillation, and that is not desirable because there will be always mismatch in the timing and this. But how to reduce that effect? One way, you can have a very high sampling rate so that you can effectively reduce the time, and many commercial products use that. Okay, they use an oversampling for constant on time or off time, but you are essentially increasing the sampling rate, means your computational rate is also increasing, so your power consumption will increase. In order to do that, there is a way to avoid, is called event based sampling. So, instead of using a fixed frequency clock, you can detect an event, and this is an ideal condition at drawing. So, event will be triggered once, either once the off time is, that means when the starting of the off time, or it can be even taken at the end of the off time. That means we can associate this event with the timer either activation or deactivation. That means activation means when the timer is enabled, monoshot timer, or when it is actually your counting is over, or it can be in between anywhere. And you may ask what will happen. First of all, you cannot exactly take the sample right at the point of switching, because that will introduce a lot of noise. So, you should avoid that switching. So, you need to shift the sampling rate, and we will discuss this practical aspect in the subsequent architecture. Then the next question, what will be the impact of stability? So, we have not gone to that level, and we may not discuss many stability aspects in this course, but we want to give you some basic thought. Particularly, we want to highlight the fixed frequency modulation. If one understands thoroughly, then he may try for the variable frequency for going detail. Okay, so event based sampling, it will synchronize with the event rather than time. So, you will eventually get one sample per cycle, and you can see always there is a fixed interval between the sampling point and the on pulse, trigger pulse. So, that the delay will be fixed because you are taking with respect to an event. Similarly, if you talk about constant on time, where the on time is fixed, but off time varies based on, because if you take the valley current mode control, and this is a very popular method for commercial product. Okay, so here this time is fixed, this time is fixed, this time is on time, this is fixed, and we generally take the sample. Where we should take? We can take sample here or sample here. So if you use a uniform sampling, then you can see this is the duration between interval, and here it is sampling here. So that means sometimes it is sampling at the on time, sometimes it is sampling the off time, or the duration between the sampling point and the switching point is varying. So naturally this will lead to multiple limit cycle oscillation, but again in order to stabilize, we can synchronize with the timer. That means here we are taking the sample when the timer actually finish the counting. So it is synchronized. For the other case also, we could take when the timer is enabled or disabled, but we need to check which one is best in terms of stability point of view. Okay. So this is like a constant on time, and it is event based sampling. So by taking the right event, we can, in this case, since you are taking the sample after the on time is elapsed, so you see this difference, that means the difference between the turning on of the switch and the sampling point, they are always constant. So this is the event that we have selected. If you select this event also, so they are synchronized with this clock, trigger clock. So again this is not a switching clock, it is a trigger clock, because this trigger clock is enabled when the monoshot timer is enabled. That means when the current will touch the valley current. So this is the event which will generate this trigger pulse. This trigger pulse will be enabled here. So this trigger pulse. Leading edge modulation. We have discussed about trailing edge modulation. Leading edge, what happened? We generally at the rising edge of the switching clock, we generally turn off the switch. And our valley current mode control is a good example of leading edge modulation. And for leading edge modulation, again if you take one sample per cycle, you can take the sample right when the switch is getting turning off. Okay, and again you can insert a delay. Okay, interval 1 sampling, so you can insert a delay. So here we call it as a interval 1 sampling. So this delay is inserted. That means we have inserted a delay. This is to accommodate the conversion and the computational time, and we will go for a practical converter example that will be very clear. But this lecture we are emphasizing the typical waveform of the voltage and where to sample. So it is equally important, the rate of sampling as well as the timing of sampling is very important, and that will actually affect in terms of regulation, in terms of stability. There are many aspects will come. Then you take a boost converter. If you take a boost converter trailing edge modulation, so ideally if you sample at this point, then this is a practical boost converter. Now the practical boost converter has a ESR jump. So it is not recommended that you take the sample here, but it is just for starting the concept. We are as if taking one sample per cycle, but practically you should introduce a delay. That means you should take the sample earlier than switch turns off. That means before the switch turns off, we should introduce a delay, and this delay can be easily inserted in your HDL code, because you will have a fixed time period, and after this time period every time you actually, that means you have to create this sampling clock, and you need to create a phase shift, time shift with respect to the switching clock, and then you can just send the command. So this clock will be sent to your A to D converter, and then after this time of delay time, this is a TS delay time, you can actually, it should complete both conversion of the ADC as well as the computational time. So that's why we have to vary the delay based on what sampling rate you are using, what is the conversion time, and the conversion time of the ADC also varies based on the architecture of the ADC. If you are using pipeline ADC, then the conversion time depends on the number of pipeline cycle. If you are using flash ADC, it is very simple, but it is rarely used in commercial product because of a high resource cost, right? That means the cost is high. or you can use simply successive approximation ADC. So, there are many architectural ADC, but only thing we need to know, there should be sufficient sampling delay, so that it can complete the conversion as well as the computation in the digital controller. Another interesting point in the boost converter, if you take the sample here, the boost converter actually suffer from right half plane 0. So, whether should we take the sample point at the peak voltage or the valley voltage, that may slightly affect the RH0 effect, and there are research paper on this, but we are not going to discuss. When we come to boost converter, this current mode sampling, we will discuss some aspect there. But the selection of the sampling point is also very important for a boost converter in terms of its small signal performance as well as in terms of the first scale stability. And what do you mean by first scale stability? That we will discuss when we go to mathematical modeling, or I will show in subsequent lectures some MATLAB simulation case study to give you an idea what do we mean by first scale stability. So, in summary, we have shown steady state operation of switch mode power converter, various fixed frequency and variable frequency modulation techniques are discussed. We have shown some basic sampling mechanism, whether it is a uniform sampling or event based sampling. Then where should we sample, because you need to accommodate the delay for the conversion and computation time. Then we have also discussed some uniform and event based sampling method. So, in the coming lecture, we will be talking about how can we incorporate this and come up with the architecture. Today I think we got some basic idea about the sampling mechanism. That is it for today. Thank you very much.